Welcome to Easy Math TV. We're going to continue our statistics series using Excel to understand properties of statistical values and what those statistical calculations are used for. In this case, we're doing a series on confidence intervals. This is the second video on the confidence interval of a mean. So in the first video, right before this one, we used a different method. We used the Z method. We calculated a Z value to get a confidence interval for heights in inches. And in this case, we knew what the population standard deviation was, sigma. And we also we're pretty confident that the original population was, in fact, normally distributed. So those assumptions were necessary in order to use that method that we learned about. But this particular method here does not require any of those assumptions. We don't need to know what the population standard deviation is. We don't need to know anything about the population. All we have is a sample that we've taken from that population. So let me just mention at the outset here, the advantage of this particular technique is that no assumptions need to be made, and we don't need to know anything about the original population X. The only disadvantage is that we tend to get wider confidence intervals as a result. So it makes it hard to make precise assertions about the population. We won't be able to be as precise as we would normally be if we knew more about the population. Okay, so there are advantages and there are disadvantages, but this is also the more common approach that you will find in the literature, in the research, because we really can't. Oftentimes we just can't make those assumptions about the population. It's a very uncommon thing to be able to assume that your population is normal. You can also see that we're working from data here. That's not necessary. It doesn't require that you actually have data that you put into Excel. You could use a different tool to calculate the sample mean and the sample variance, as well as the sample size. Those are the three things that you can use something else to calculate those things, and then just type them in here. But we're actually putting all of our data into column A, and then we're just going to work from our data. So the way you see me set up these spreadsheets is that I typically will put my headings across the top, and that's no exception here. So I have my heights in inches in column A. In columns C and D, these are my calculations. And then in columns F, G, H, and I is my information about the confidence interval itself. So what you see here in column C, these are just typed in. I've typed in descriptions of every calculation that we need to make, and you can see there's a lot, so we should just get right into it. The first calculation is for the sample mean. So you're either going to calculate this or you're just going to type it in. And I've typed it into cell D3. That's just our average calculation. So if you've seen previous videos of mine, you've seen just that we know how to calculate an average at this point. That is our sample mean. So my data is in cells A3 all the way down to A32, and you can see that inside the parentheses there. To calculate the sample variance, again, we use the Excel formula var.s, var.s. So, and you have to type an equal sign in front of any formula that you use in Excel just to remind you, and then your data goes inside the parentheses. In cell D5, to calculate the sample standard deviation, we just take the square root of that number that we just calculated in D4. So in cell D5, type equals SQRT, parenthesis D4, close parenthesis. And the sample size is again, you can either just type this in yourself, or if you have the data in column A, you get your sample size by just using the Excel function count. So it's equals count, parenthesis, and then A3 down to A32, close parenthesis. And it just so happens that I have 30 values of data. So these are heights in inches of soccer players. Then in cell D7, based on the sample size that we just typed into D6, we have to take the square root of that. So equals SQRT, parenthesis D6, and that goes into cell D7. Our population standard deviation is typically unknown. It could be known, it could be unknown, it doesn't matter. So I'm just going to type unknown there because we do not know it. And then the other thing that we need for this particular method is something called degrees of freedom. That takes a lot longer to explain than it is worth explaining right now, but it's basically one less than your sample size. So we have to type equals D6 minus 1. So it's always your sample size minus 1. That is the degrees of freedom. And that's going into cell D9. The confidence level was just typed in here, and the standard is 95%. If you don't know what it is, just type 95%. But if you're given what the confidence level is, then that's what you would type in here into cell D10. The standard error of the mean, then, that's in cell D11. That's equals D5 divided by D7. So in this case, instead of taking sigma and dividing by the square root of n, we're taking our value of s. Lowercase s is our sample standard deviation. And we're taking s and dividing by the square root of n. Then we have something called a cumulative probability. The cumulative probability is necessary to find the right t-value that we need, the correct t-value. So the cumulative probability is equals our confidence level, D10, plus 0.5 times parenthesis 1 minus D10, close parenthesis. So we need the confidence level plus the area of the left tail. So remember, the confidence level is an area. It's an area at the center of the curve, which means that whatever's left over gets split half and half on both sides. So you have half of the remaining 5% is on the left, and half of the remaining 5% is on the right, and we want to include the half that's on the left. So again, that's equals D10 plus 0.5 times, parenthesis, 1 minus D10, close parenthesis. So half of 5% is 2.5%. So 95% plus 2.5% is in fact 97.5%. So we did get the correct value there. And then the last calculation we need is our actual t-value, t-statistic. So that's in cell D13. Type equals t dot inv, parenthesis, and we need two things. We need the probability, or the cumulative probability in D12, comma, and then our degrees of freedom in D9, and close parenthesis. So our t-value just happens to be roughly 2.04, 2.045. And that's a reasonable number to get, because it should look like a z-value. So the true mean mu is going to be centered at x bar. X bar was what we call our point estimate of the true mean. That's where we start. That's kind of our point of reference. And the true mean is going to be somewhere on either side of that number within some margin of error, right? So the margin of error of the mean is our t-statistic times the standard error of the mean. That's what we call margin of error of the mean. And so you can see what the confidence interval sort of looks like here on a number line with x bar at the center, and then x bar minus t times SEM on the left, and x bar plus t times our standard error of the mean on the right. Lower limit and upper limit. So let's calculate those two things. The lower limit then is equals D3 minus D13 times D11, because that's where our x bar and our t value and our standard error of the mean are. They're in those three cells. And you'll notice the subtraction there because it's the lower limit, so we have to subtract. For the upper limit, we have to add, so it's equals D3 plus D13 times D11, and hit enter. So this is what we would state. This is what we would say about that. Actually, let's just scroll down and we'll talk about it. So from this sample, we get a 95% confidence interval, which you see here inside of brackets. So I just use square brackets, and the lower limit is 64.708. I've rounded that down, and then comma, and then the upper limit is 66.091, which I rounded up to the nearest thousandth. So what that means is that 95% of all samples from this population, as long as it's a sample of size 30, right? So take a sample of size 30 and just keep doing that over and over and over again. 95% of all those samples from this population will have a mean that falls inside this interval. So the true mean, then we can conclude, is bigger than 64.708 and smaller than 66.091 with a confidence of 95%. So we have with a probability of 95%, that statement is true. The probability of that statement being true is 95% or 0.95. So basically, confidence intervals are used to determine if an observed result is statistically rare or not. So suppose someone takes a sample and calculates the mean and gets a mean of 65.7. Is that considered to be statistically rare? No, because it is inside of our interval, right? It's bigger than 64.708 and it's smaller than 66.091. So that is not statistically rare. However, if we took a sample of size 30 from this population at random, just one sample, and calculated x bar and we got 63.8, what does that indicate to us then? Well, with 95% confidence, this would be considered to be a statistically rare event. And we would have sufficient reason to believe that perhaps using that sample mean of 65.4, so the previous sample that we used to construct the confidence interval, might not have been a good choice. That the true mean is not in fact centered at 65.4, but is centered at a different value than that. Okay? So that's what one sample being outside of that range is sufficient to suggest that that our confidence intervals should be centered at some different value. Okay? All right. So like, subscribe, comment down below if you're finding these videos helpful. If you find that it's helping you to understand the statistics, not just calculate things randomly, um, and share these videos with other people that are taking statistics for the first time. I'm really hoping to gain an audience on YouTube so that I can start creating more content. And I'll see you in the next video.